In this video, we're going to go over how we measure concentration of fluids within the body. And we use two basic units. We use osmolality and osmolarity, both of which are concerned with how many solutes we have in our body fluids. For example, we're going to look at the kidneys. Kidneys have nephrons, and nephrons filter the blood, remove waste products that winds up in your urine. Well, look at this. Here's a nephron, and this is showing this loop of the nephron here, and what do we have showing the concentration of the filtrate coming through the nephron? It's in milliosmoles. This is how we measure solute concentration, and we're going to be going over detail of that in this video. It's also involved, for example, when we're talking about, in a previous video, how your body regulates your blood pressure in relation to fluid volume. Remember, we talked about the hypothalamus. The hypothalamus regulates your concentration within your blood, which is how much solutes you have. Well, if you begin to sweat, if you're losing water, then you're going to have your osmolarity is going to increase because you're losing water and your solutes are becoming more concentrated. Well, the hypothalamus has osmoreceptors, remember those? Because they're measuring osmolarity of the blood. They have those receptors, and that's going to tell your hypothalamus that you're losing fluids or your body fluids are becoming more concentrated, in which case the hypothalamus is going to make more antidiuretic hormone. This ADH is going to be released by the posterior pituitary gland, go through the blood, go to the kidneys, and increase the reabsorption of water. And you also have the hypothalamus telling the higher centers of the brain that you're thirsty, so then you drink more water. Both the increased water reabsorption at the nephron and the drinking of fluids, it's going to raise the amount of fluid and thus decrease your osmolarity. It's a negative feedback mechanism. We're going to go into a lot of detail about this throughout the semester when we're looking at these concentrations. So let's get a basic understanding of what these concentrations are. So when you look at the measurement of body fluid concentrations, in physiology and medicine, osmolality and osmolarity are used to measure solute concentrations of body fluids. These are usually the plasma and the urine. They are technically different, but because of the relatively small solute concentrations measured in the body, they're functionally the same and oftentimes are used interchangeably. When we look at osmolality versus osmolarity, well, just by letters, osmolality has an L, where osmolarity has an R. You can see here's the L and here's the R. Osmolality is the number of solutes measured in osmoles per kilogram of solvent, so it's osmoles per kg. Osmolality of plasma, you want to star this in your notes, is 275 to 295 milliosmoles per kilogram of plasma. Now I have 300 in parentheses because I've seen other sources quote 300 milliosmoles as the reference number. That's a little bit more than what we have in our textbook, so make sure you memorize this range, but realize you could also have 300 as well. Osmolarity, which has that R, is the number of solutes or particles measured in osmoles per liter of solution. And we designate that as osmoles per liter or capital OSM per liter. Osmolarity of plasma, again, same concentration. 275 to 295 with 300, well, just similar to what I mentioned about osmolality. And this is 275 to 295 milliosmoles per liter of plasma. And we use milliosmoles per liter because the solute concentration in the body are relatively small. So 1 milliosmol is 1,000th of an osmol. When looking at molarity and molality, what's the difference between these two? Well, if I was going to make a solution using molarity, I would take the substance that I'm going to mix into the solution. I take a mole of solute A, I put it in the container, and I fill it up to the 1 liter mark. Here's another mole of solute. I take a mole of solute B and I put it into the beaker and I fill it up to 1 liter. Well, these substances that are in here are taking the room of water, but you still fill it to the 1 liter mark. I don't add any more water, even though these substances, which are larger, are taking more room, so there's actually less water in here relative to the substance, but I'm filling it up just to the liter. In molality, look at what we're doing. I take a mole of solute A and I'm going to add 1 kilogram of water, which pure water comes to 1 liter, but I'm going to add that. So regardless of how much room this mole of solute A takes up, I'm going to put a whole kilogram of water in there, even if it goes past the 1 liter mark. And if I have larger solute molecules and I take a mole of solute B, which has the same number of particles as mole of solute A, they're just bigger, and I add 1 kilogram of water, it goes even higher above the 1 liter mark. Because when you're dealing with molality, you add 1 kilogram of water to whatever the mole of solute that you're mixing in there. So it can go above the 1 liter mark. Well, the human body, the concentrations we're dealing with, you're not going to have this really large over increase above a liter when you make a molar solution, when you use molality versus molarity. When you look at molarity versus osmolarity, molarity is a number of moles of solute dissolved in 1 liter of solution. Units are moles per liter, or can be abbreviated as capital N for molar. A mole just equals 6.02 times 10 to the 23rd particles. These particles could be atoms, they could be molecules, ions, electrons. The value of 6.02 times 10 to the 23rd is known as Avogadro's number. So 1 mole of a substance is equal to that substance's atomic or molecular weight, and molecular weight being the sum of the atomic weights for each atom in the molecule. And we use the periodic table in order to get these atomic weights. Well, you're not going to have to go through in physiology and make molar solutions. This that you have in your notes is just an FYI on how to do that. And I'm using sodium chloride as an example. When you take chemistry, you'll learn all the details of this. But what you do need to appreciate is that when we're talking about osmolarity, it's similar to molarity, except that it is a measure of the number of osmotically active particles, or ions or molecules, per liter of solution. And what do we mean by osmotically active particles? Why do we add the os to osmolarity? Because that os means osmotic effect. These are osmotically active particles that contribute to osmotic pressure of a solution. So they can affect osmosis. And that's what we're concerned with the body, is that when you put these solutions in there, or you look at the solution concentration, how does it affect osmosis? And we saw when we went over osmosis, you can shrink up cells if you put them in a hypertonic environment. You can swell cells and possibly burst them if you put them in a hypotonic environment. And then if you put them in an isotonic environment, you have fluid moving in both directions equally. So it greatly affects the cell dealing with the environment they're in. So we have to know the concentrations of these environments. Or if we're given an IV, we need to know the concentration of that IV. Well, how do we measure these active particles that can affect osmosis? We classify them as osmolality, osmolarity. Let's take a look at an example of an ionic compound. Although adding 1 mole of sodium chloride to enough water to make a 1 liter solution makes a 1 molar solution, it makes a solution with an osmolarity of 2 osmos per liter of osmotically acting particles. The reason why we have 1 versus 2 osmotically active is because sodium chloride dissociates when dissolved in water. This means that although when dry, the ionic compound sodium chloride is considered 1 particle, as shown here, when dissolved in water, sodium chloride is going to split apart. We say it dissociates, and it dissociates into 2 particles, 1 sodium and 1 chloride ion. The osmo and osmolarity means that we are accounting for each ion as a separate particle and its effect on osmotic pressure in the cells of your body. Thus, sodium and chloride has twice the osmotic pressure as sodium chloride that is not dissociated, and we have to take that into account when we're adding ions to solutions. Well, here's a question for you. Which would have the greater effect on osmotic pressure? 1 glucose molecule, which is a large molecule with 6 carbons, 12 hydrogens, and 6 oxygens, and you dissolve that in water, this 1 glucose molecule, or 1 sodium chloride, which will dissociate into individual sodium and chloride ions. Which one would have a greater effect on osmosis? Answer: sodium chloride. Even though sodium and chloride are a lot smaller than glucose, the size isn't the factor here. It's the number of particles. And when you dissociate this 1 sodium chloride into sodium ions and chloride ions, each has an effect on osmosis. So this 1 sodium will have the same effect as 1 glucose. Now, if you have sodium chloride, you've got twice the effect having sodium chloride dissociate as to 1 glucose molecule. So here's some practice problems for osmolarity, like you'd expect to get on a quiz or an exam. If I put 2 moles of sodium chloride in a 1 liter solution, how many osmos per liter is that? Sodium chloride dissociates completely to sodium and chloride ions. Answer: 4 osmos per liter. Well, how do I get that? Well, if I have 2 moles of sodium chloride and sodium chloride dissociates into 2 sodium and chloride ions, I just take the 2 here and I multiply it by however many moles I'm putting into the solution. So 2 times 2 is 4 osmoles per liter. What about 2 moles of glucose in a liter of solution? Glucose doesn't dissociate. That glucose stays together. So if I look at this, even though it has all of these atoms that make up glucose, they don't break apart in solution. They stay as one molecule. So what would this be? 2, because it's not going to dissociate. So if I put 2 moles of glucose in a liter solution, I'm going to get 2 osmoles per liter. What about a mole of magnesium chloride in a liter solution? Well, magnesium chloride dissociates into 1 magnesium, and since I have a 2 right there, that means there's 2 chlorides. So you get 2 chloride ions. What would this be? 3. Because I go 3 here times 1 mole of it gives me 3. Now what if I had 2 moles of this? Well, this would be 6. Well, what if I had 3 moles of magnesium chloride? Then it would be 3 times 3 would give me 9. What about this one? What if I have 2 moles of calcium chloride in a liter of solution? What would that one be? 6. Why? Because calcium chloride, you get 1 calcium, 2 chloride ions, they dissociate, you multiply it by 2, and you get 6. Now for testing purposes, I'm either going to give you glucose or another salt. And the other salt, even though there are salts that don't completely dissociate, the ones I'm going to give you completely dissociate in water, so you can use the same type of calculation. So whatever salt I give you, even if you haven't seen this salt, say calcium chloride, you've never seen it before, you should know that when you put it in solution, calcium is going to dissociate from the chloride ions, and that little 2 right there tells you that there's 2 chloride ions and 1 calcium ion that you'll get from this. A summary of osmolarity versus molarity. Well, osmolarity is distinct from molarity because osmolarity measures the total concentration of all the solute particles in a solution that are osmotically active. Molarity just measures the moles of a solution per liter of solution. The distinction arises because some compounds can dissociate in a solution, whereas others cannot. When we're talking about glucose, that's an example of a non-ionic compound. It doesn't dissociate. Thus, for each mole of solute, you're going to get 1 osmole per solute. For example, 1 mole of glucose equals 1 osmole. Multiple compounds may contribute to the osmolarity of a solution. For example, if I want 3 osmole solution, this might consist of just adding 3 moles of glucose. Or you can add 1.5 moles of sodium chloride. Why would that work? Because 1.5 and sodium chloride dissociates, so that's going to give me 1.5 moles of sodium, 1.5 moles of chloride, together gives you 3 osmoles. Or you can put 1 mole of glucose and 1 mole of sodium chloride. That's going to give you 3 altogether. Or 2 moles of glucose and a 1/2 mole of sodium chloride to give you that same 3 osmole solution. Here's a good thought question on why our cells, when we store glucose in our cells, the cells actually use ATP to take the glucose molecules and hook them together to form glycogen. Remember, glycogen is a storage form of glucose in animal cells? Well, why does it do that? Why does it use energy to hook these up together to make a big old glycogen molecule? And then when you use the glucose, you got to break them apart, which means you got to use energy to break them apart. Well, the reason is that when you hook the glucose together to make glycogen, this one big glycogen molecule has the same osmotic effect in the cell as one glucose molecule. Doesn't matter about the size, it matters about the number. So the cell's going to hook all of these together so that it doesn't have a huge osmotic effect on the inside of that cell. If it left them all apart, all these glucose molecules apart, then that would have a bigger osmotic effect, a lot bigger osmotic effect than just have them all hooked together as one glycogen. And here's this dark granule of glycogen in the cell. Osmosis is really amazing in its effects on the cell. So that's why we're spending some time on this. Let's test our knowledge. Measurement of body fluid concentrations, part 1. You want to select the term that makes the sentence correct. Go ahead and pause the video. Here are the answers. Part 2, go ahead and pause the video and select the correct term. Here are the answers. Here's part 3, go ahead and pause the video and select the correct term. And here are the correct answers. And this concludes the video. If you have any questions, let me know.